Okay, so on your Cornell note sheet, please put today's date, put your name, put the topic. The topic today is waves. And your class subject, obviously, is science. Okay, so please put the heading / title on your Cornell notes. Okay, remember that your big ideas go on the left, in that left-hand column. Okay, and all the detailed information, okay, can go on the right. Okay, let's get started. Okay, so waves. Notice it's in green, and you need to put that main idea in your left-hand column. A lot of the main ideas are going to be in green on this slideshow. Okay? Notice the details about the green is underlined. Okay, so what are waves? Well, they carry energy. Okay, waves, they come and carry energy from one place to another. That's what a wave does. Carries energy, transfers energy, moves energy from one place to another. Okay, and I know this is really abstract because you can't see them. You can't see the sound waves that are traveling across the room. Okay, but they're there. Okay, so waves are classified into two main types of waves, and they're classified by what they move through. Okay, so today we're mostly going to talk about mechanical waves. Okay, mechanical waves. What's really interesting about the mechanical wave is that in order for it to move, it has to attach itself to some sort of matter. Okay, in order for that mechanical wave to move, it has to have matter. So that matter could be the air, that matter could be the earth, matter could be the water, matter could be the human body. Okay, but in order for that mechanical wave to transfer its energy, it has to attach itself to matter. Now there's another type of wave that is completely different from a mechanical wave. It's called an electromagnetic wave. And electromagnetic waves, or EM waves, they do not need matter to move. Now they can move through matter. Electromagnetic waves, they can move through matter. But they don't have to have matter to move. So electromagnetic waves are really useful in outer space where there is no matter. It's just the void of space. Okay, so your mechanical waves have to attach themselves to matter. Your electromagnetic waves do not. Okay, and during this presentation, we will not go into detail about electromagnetic waves. That is a completely different PowerPoint. And if you are dying to know more about electromagnetic waves right now or tonight, you can get on my website and you can look at my electromagnetic waves PowerPoint. Okay, but for today, we're mostly going to be talking about those mechanical waves. Okay. May I move forward? Okay, let's talk about wave structure or wave anatomy. Okay, go ahead and draw your wave and put a baseline through it. So that line through the middle, that's called a baseline. And you can go ahead and label that as a baseline if you want to. And I want you to think about all the places that you've seen this wave, or a wave that looks like this. Think about all the places that you've seen a wave that looks like this. Okay? I don't know about you, but when I see this kind of wave, I immediately think of like a heart rate monitor, okay? Or when a woman is in labor, the doctors will hook her up to a machine to monitor the baby's heart rate, okay? And as long as there is a wave being produced by that machine, that means that the person's heart is beating, okay? You've all seen on those, medical TV programs when somebody flatlines, when there's no longer any wave. There's no longer any energy being transferred by the heart, and it flatlines, okay? And there's no longer a wave. You just see just movement along the line, which means the heart is no longer beating. Not good. Okay. So the first thing that we are going to label, first three things, excuse me. Go ahead and label your crest or peak, okay, which is the top of the wave. Go ahead and label your trough, which is the bottom of the wave. Okay, and then we're also going to label our amplitude. Okay, so amplitude is from the rest line to the crest, or it could also be measured from the rest line to the trough. Okay, that would be your amplitude. And amplitude will tell you how much energy the wave is carrying. So the higher the amplitude, the more energy. Amplitude related to sound waves, okay? If the higher the amplitude, the louder the sound. The lower the amplitude, the softer the sound. Okay, and you can remember that by when people play guitar or instruments, they hook their instruments up to an amp to make them louder, to increase the amplitude of their instrument. Okay? And obviously, there's a lot more energy coming out of a really loud instrument than an instrument that is playing softly. Okay? The next part of the wave that we are going to label is called a wavelength. A wavelength. Okay, and wavelength could be measured from crest to crest, from trough to trough, basically two corresponding parts on that wave. Okay, low energy waves typically have long wavelengths. High energy waves typically have short wavelengths. Okay, now that we've covered wave anatomy and you know all the different parts of the waves, we're going to go back to mechanical waves. Okay, there are going to be 3 different types of mechanical waves that we're going to talk about. But before we talk about them, we're going to go over some terminology that you need to know in order to discuss waves academically. Okay, so as we know, mechanical waves, they travel through matter. You do not have to write that again, but notice it's there again, so maybe put a star by it because it's important. So go back up into your notes and put a star by that because if you're seeing it again, you know it's important. Okay, let's talk about this word medium. Mechanical waves need a medium to transmit energy, to move energy. Okay, the word medium is not talking about the size shirt or pants that you wear. Okay, it's another word for matter. Okay, the medium is the material that the disturbance is moving through. Okay, so think about earthquake waves. What would the medium for an earthquake wave be? Think about earthquake waves. What would that medium be? Okay, if you're thinking that the medium for an earthquake wave would be the earth, you are correct. Okay, let's do another one. What is the medium for an ocean wave? Think about what a medium for the ocean wave is. The material that that wave is moving through. Okay, the medium for an ocean wave would be water. Okay, let's do one more before we move on. Okay, think about the medium that sound waves travel through. What is the medium that a sound wave travels through? Okay, if you said air, you are correct. Okay? Okay, so that's a medium. Matter, the matter that the wave travels through. Remember those electromagnetic waves, they don't have to have that medium. They don't have to have a medium. They can travel through medium, they don't need them. Only those mechanical waves. Okay, this is kind of a duh thing. I don't know. As a wave travels through the medium, it eventually loses its energy. You see that quite clearly if you take a pebble and you drop it into a pond. The amplitude of the wave is very high at first, and then as the wave moves, okay, it loses its energy and it gradually dissipates. Okay? That happens with water. That happens with sound waves. It can happen if you're moving a rope. One more term, okay, that you will hear during this unit is the word pulse. And basically, it's that initial movement that creates the direction of energy transfer. Okay? So during an earthquake, a pulse would occur at the epicenter of the earthquake. Okay? This person in this slide who is holding the rope, he's creating a pulse and sending the energy in a particular direction. You drop that pebble into the water, the lake outside, back behind your house. Okay, you're creating a pulse. You're sending energy in a particular direction. So there's some just, stuff that you need to know in order to talk about mechanical waves academically. So now that we've gone over wave anatomy, we've gone over academic terms, let's actually talk about the 3 different types of mechanical waves. So on your notes, I want you to kind of just visualize 3 different sections. Okay, so these are the 3 different types of mechanical waves that we're going to talk about. Okay, so kind of leave some space to kind of jot down information about them. Okay, because obviously I'm going to tell you I'm going to tell you the 3 types of mechanical waves, which are longitudinal, transverse, and surface. And then we're going to go and we're going to discuss each one of them individually. So on your notes, please make sure that you're leaving room to jot down more info. Okay. So the 3 different types of mechanical waves, the 3 different types of waves that have to have a medium to move are going to be longitudinal, transverse, and surface. Okay, and they're classified by the way they move. Okay, so here's some information about longitudinal waves. Now it's just a little snippet. Okay, make sure you leave enough room to be able to go back and add to it. Okay, so your longitudinal waves, the vibration is in the same direction as the wave pulse. They actually move parallel. Okay, so it moves back and forth in a back and forth motion, in that parallel motion. Okay, back and forth, back and forth. That's your longitudinal wave. The source moves right and left. Okay, it could also move up and down. Longitudinal waves. I want you to kind of start thinking about waves that you hypothesize move in a longitudinal way, or would be classified as a longitudinal wave. Start kind of like thinking about that. Okay, the next type of mechanical wave is going to be your transverse wave. Transverse. Okay, notice that the transverse wave has the same, it looks like a snake moving through the grass. Okay, snakes, they traverse. Transverse waves look like snakes. Okay, most waves that you probably think about would be classified as a transverse wave. And a transverse wave, that vibration is at a 90-degree or right angle. Okay? And once again, transverse waves, they can move, mostly they move across. They can move up and down though too. Okay? The last type of wave, which we're not going to spend a whole lot of time on, is called a surface wave. And that's where your vibration would be circular. The vibration is only taking place at the surface of the medium, like in the ocean, or maybe even a pond. Okay, so now that we talked about the 3 different types, we're actually going to go, in the next slides, the following slides, we're going to go and talk about each one of them in detail. Okay. The first type of wave is going to be your longitudinal wave. So remember we said the vibration is parallel. You're seeing that again. It's important. Underline it. Okay, on your test, in your vocabulary, the definition, it will use the word parallel. So the vibration being parallel, keyword, to the direction of the motion of the wave. Okay, with a longitudinal wave, there is this back and forth motion, like this, or like this. Okay, this back and forth motion. Okay, and hopefully you've identified 2 of your vocab words, compression and rarefaction. Compression meaning pushing together. Rarefaction meaning pulling apart. So with a longitudinal wave, there's this constant compression and rarefaction. Hopefully you've had an opportunity to kind of hypothesize some longitudinal waves. Let's see if your hypotheses are correct. Sound waves are longitudinal, are classified as being longitudinal. And then also P-type earthquake waves. So earthquakes, they give off a couple different types of waves. P waves stands for primary wave. So that P-type earthquake wave would also be considered a longitudinal wave. Okay, and then down here, you can see rarefaction and compression on the slinky. Okay, and slinkies are really good examples of longitudinal waves, but you can also make a slinky, the other type of wave. Transverse. No, I am not perfect. Okay. Next, let's talk about, excuse me, the transverse wave. Because remember we said the transverse wave, it makes a motion similar to a snake that is traversing through the grass. That vibration is perpendicular. It's at that 90-degree angle, so you, once again, you're seeing that again. You know it's important. Maybe underline it, highlight it, or put a star by it. Transverse waves, they can move sideways. They can move up and down. Some examples of some transverse waves would be your S-type earthquake wave. So S-type would stand for your secondary earthquake wave. And then also electromagnetic waves would be considered transverse. Those radio waves, those microwaves, they have that transverse movement, motion. I want you to think about some other transverse waves that you might know of. Or maybe something that makes a transverse motion even. Okay. Here you can see the waves moving sideways or up and down. Okay, here are your P waves. Just a little, you don't have to write anything down for this. Waves that describe the earth, your P waves, they move through solids and liquids. Your S waves, they move through solids only. And that wraps up this portion of your Cornell Notes. Thank you for listening.